So, hi, welcome back to the series where we are writing an operating system in Rust. Today, we are going to talk about CPU exceptions. So, if we go to the list of the post, we have explored a Rust binary, minimal Rust kernel, a VGA text mode, and so testing I am skipping for now because in testing we are actually doing a test framework setup for our no standard environment. We Today we are going to talk about what is a CPU exception and how can we handle CPU exceptions for our operating systems. And let me just start the timer also because I don't want to extend the timer in today's case. So what I'll do is I'll just reset it and start it. So okay. So yeah, and I have created some of the notes for today's talk. So and in the layman language or in layman terms, a CPU exception is nothing but a scenario where something is wrong with the current execution. For example, some invalid instruction is being executed, or something is being done with which is related to a divide by zero type of error has been occurred. So such type of error scenarios are nothing but an exception, and CPU or our operating system needs to handle such exceptions gracefully. So for an example, whenever we try to divide by zero in our normal operating system or in our general purpose operating system, the operating system has an inbuilt exception handler, and that gracefully handles our exception and spits out the required error message. So in the similar way, our operating system also needs to handle such exceptions and throw out an information to an user that particular exception has been occurred, and here is where the program have panicked. So let's talk about exception. There are 20 different types of CPU exceptions for x86 architecture. Uh, some of the types are page fault. For example, whenever we try to access an illegal memory, then page fault exception occurs. Invalid opcode. If we try to execute some instructions which are not available for that particular architecture, then in those such kind of exceptions are invalid opcode, general protection fault, double faults, triple faults. Double fault is very interesting. Whenever an exception occurs and our CPU tries to execute an exception handler, and in this process another exception occurs, then that such kind of scenarios are called as double fault. And triple fault is again one step ahead. While calling the exception handler for double fault, and in that process again an exception occurred, then it is a triple fault. And triple fault is non-recoverable exception. It basically directly leads to system reset. So we should definitely avoid triple faults. Now, what is an interrupt descriptor table? How So just think of it in layman terms. If an exception occurs, there must be the information somewhere present for the CPU to know that this particular exception has this particular function handler for that exception. So all that this kind of table is already present in an operating system that is called as interrupt descriptor table, and we also need to create an interrupt descriptor table for our OS. So what is the structure of that? We'll just have a look at it very quickly. So it is a 16 byte structure. The first 2 bytes are function pointer to the handler function. Then the next 2 bytes are GDT selector. It is a selector for the code segment in the global descriptor table. Then again, second 2 bytes are some options. Option have this following structure. So first 2 bits or first 3 bits are interrupt stack table index. What is the interrupt stack table? Do we need to change the stack table? Then 3 to 7 are reserved. Eighth bit talks about interrupt gate, whether interrupts will be disabled or interrupts will be enabled throughout the execution of this particular exception, and so on. And finally, what is the privilege level of this particular exception handler? The next 2 bytes are again function pointer, and finally last 4 bytes are also function pointer. So you see that this particular is the definition or structure of our interrupt descriptor table. Now we can see that this particular interrupt descriptor table we need to create for our operating system. That is clear. But are we going to create it by our own? No, we are going to use it. We are going to use a crate, that is x86 that we have already included in our operating system, and that crate has defined an interrupt descriptor table struct for us, and we are going to use that struct only for handling the exceptions. So if you closely look at this interrupt descriptor table, it has all the entries of the exceptions, and each exception has a type of entry which wraps a handler function. Now this handler function is of type. It is an external function of type x86 interrupt, and it takes an interrupt stack frame. So the fields are of type IDT, entry, and F is of type handler function. So what they are talking about is here is some entries have handler function, and some entries have handler function with error code. So the only difference is this kind of entries needs to accommodate the error code or error scenarios also, in order to give the information to the user that this exception has been occurred because of this error. So that's why their specific handler function needs an input of error code as well. So that is the only difference. And let's now talk about calling convention. So calling convention is again very similar to the function calling convention. That is when a function is called with the call instruction, but an exception is occurred. Exception can occur anywhere in between the execution flow. So what is the calling convention for a normal function? The first 6 integer arguments are passed in registers. So the function, if it has more than 6 arguments, so first 6 arguments are passed with the registers. Additional arguments are passed on stack, and the results are returned with these two particular registers, RAX and RDX. What are preserved registers and stack registers? Preserved registers are the registers with which we can preserve the state before jumping to the function call, and scratch registers are the state registers which are used to return back from the callee function. So these are there is two difference between the preserved register and stack registers. Now every time a function call is happened, preserved registers are being used to preserve the state. So as whenever we return from the function call, we can jump back to the state where we have left, and that is how we do things with the normal function call. But since in the exceptions case, we don't know at what point an exception can occur, and we cannot back up specific registers if an exception occurs. So what we are doing that we are backing up all the registers. So that is what they are talking about in this paragraph, that in contrast to the function call, exception can occur at any instruction, and in most cases we don't even know at compile time. So that is why we what they are saying that x86 interrupt calling convention is such that it guarantees that all the registered values are restored to the original values when the function returns. And in order to make it efficient, what they're doing is that they are only they are not backing up all the registers, but they are backing up all the registers which are being modified in the exception. So in this way we can make it more efficient as well. Let me have a look at time. Okay, interrupt stack frame. Now let's talk about stack frame. Stack frame is nothing but how much stack is being needed to store the old stack pointer and your new stack pointer. So in the case of normal function call, it is very simple. Your old stack pointer is here, and your new stack pointer points to the new stack frame, because they don't need to because they don't need to preserve all the states of the registers. But in the case of exception, so there are 7 or 8 steps which a CPU follows before jumping on to the actual executions of the exception. So what is the very first step? It saves the old stack pointer into an internal buffer, if you carefully see. Then it aligns the stack pointer. So what is an aligning? In some cases, when we are on 64-bit system, some of the instructions are 16-byte instructions or 16-bit instructions and all those things. So in order to align your stack pointer, this alignment is needs to be done. Then switching the stack. So this can happen in the case where we have two modes of execution, that is real mode and user mode. Basically, in Linux we have user space and kernel space. So in the similar way, if we are in the user space and some exception occur, we need to switch the stack to the kernel space. So that is the thing which they are talking about in switching stacks. Then pushing the old stack pointer. In the very first thing, what we have preserved in an internal buffer, that we are going to push in the we are going to push in the stack frame in this particular step. And the fourth step, pushing and updating the R flags registers. R flags register is nothing but a control and status bit registers. So this register also needs to be backed up. Pushing an instruction pointer. So before jumping to the interrupt handler function, we also need to restore the instruction pointer to because in order to because whenever the function returns, we'll resume our execution from this particular instruction only. Then push an error code. In the case of handler functions with error code, we need to push an error code also onto the stack frame in order to make sure that user gets the required information. And finally, invoking the interrupt handler. So in order to do all these 7 steps, we end up with this particular interrupt stack frame. So if you look at this interrupt stack frame, it is a very big stack frame as compared to the normal function call, and all these exceptions, all this information is also present in that interrupt stack frame. Now you might be thinking that how are we going to do all these things for our operating system? So thankfully, x86 64 crate, which we are using, provides abstraction for us. So we just need to call that, we just need to use those abstractions and methods for setting up the interrupt descriptor table and setting up the interrupt descriptor table and writing all the function handlers for it for the required exceptions. So let's get started with the implementation. We can just for this implementation, we are creating a different module in our source folder, which is an interrupt module. So here, if you go to interrupt, so this is the exception module. I have already written the code in the required manner. But if you want to have a walkthrough, we will have a walkthrough from this blog as well. So we are importing x86 64 structs, and from that we are importing interrupt descriptor table, and we are creating an instance of interrupt descriptor table in our interrupt.rs file. And for the testing or for demonstrating, we are handling the breakpoint exception. Now breakpoint exceptions are nothing but exceptions whenever a breakpoint is hit in your while you are debugging. So in our case, we need to generate this breakpoint with this int3 instruction in the x86 architecture. So they have also talked about how debuggers work series over here. So debugger basically works on this principle only. Debugger actually inserts this int3 instruction wherever we attaches that debug breakpoint. And this int3 instruction, that what it does, it basically halts the CPU execution at that particular instance whenever that int3 instruction is being occurred. And this is done via the exception handler. So what we are going to do is we are going to write our own exception handler for the breakpoint, and there we are going to print the stack frame. That's it. And for that purpose, the third thing we need to do is, so first thing is we have created the instance. Second is we have initialized the breakpoint handler function, and third thing is we need to load the interrupt descriptor table. So in order to load the interrupt descriptor table, what they are saying that the descriptor table should live as long as our operating system is alive. That means it should have a static lifetime. So in order to get the static lifetime, we need to make our interrupt descriptor table global static variable. And you all know that if you want to handle global statics in Rust, we need to use lazy statics. So that's what I have done. I have used lazy static initialization, and in this initialization we have created the instance, we have set the breakpoint handler, and then we have returned, or we have initialized the interrupt descriptor table as a global static variable. Now in this function init idt, we are just loading the interrupt descriptor table, and this is our exception handler. And in order to test that, what are we going to do? So this is the code for page fault thing. So, and this is the code for our breakpoint. What are we going to do? We are just printing hello world. Then we are going to do init. Now this init function is nothing but it is calling our interrupt init, and interrupt init is calling idt load. So whenever this method will be called, first it will do initialization once in the lazy in the global scope, and then it will load the interrupt descriptor table. And finally they are running it. So what they are expecting that it should print hello world, then exception occur, and they are expecting that the stack frame should be present. So let's build our